Good morning. Welcome to the webinar series of IEEE Joint Chapter of MTT EMC Islamabad. I'm Dr. Noshirwan Shoaib, the chair of the chapter, working as assistant professor at Research Institute for Microwave and Millimeter Wave Studies at National University of Sciences and Technology, Islamabad. So we are based in Islamabad. Islamabad is the capital of Pakistan. It is one of the beautiful city of Pakistan, a well-managed city. It is also one of beautiful capital of the world as well. Apart from just a business hub, it is also blessed with the greenery as well. You can see a few photos in front of your screen as well. This is the place where we will host Pakistan first RF and microwave conference next year. And we hope that most of you or all of you will come to Pakistan to visit us to join this conference and submit your papers and contributions. So National University of Science and Technology has several campuses. This is a bird overview of Islamabad campus, and we are located in Islamabad. As you can see, the building of the RIMS in front of you, which is encircled. So the Research Institute for Microwave and Millimeter Wave Study is a unique postgraduate institute that offer MS and PhD program in electrical engineering with focus on RF and microwave. We are equipped with the antenna and EMC equipment and facilities. Our anechoic chamber go up to 40 gigahertz. We have EMC My Lab. We have microwave research lab. We also have a PCB fabrication lab in-house so that we can provide the students with all the technical knowledge and practical knowledge with their theoretical knowledge as well. It's also pertinent to mention that we are the only academic institute in Pakistan to have these facilities on board, and we consider this as a national asset, and we are open to research and teaching collaborations within Pakistan and in foreign countries as well, so that we can promote our research and also to get more student placements, more visits to the foreign universities as well. So today in our webinar series, we are very pleased to welcome Dr. Goutam, who is currently working at NASA-Jet Propulsion Lab in California Institute of Technology, Pasadena, USA. The title of the talk is Are We Alone? NASA Technologies to Find Life Beyond Earth and Answer to the Other Science Questions. Dr. Goutam is a senior scientist at NASA's Jet Propulsion Lab, California Institute of Technology, and a visiting professor at the Division of Physics, Mathematics, Astronomy at the California Institute of Technology, Pasadena, USA. He received the PhD degree in the electrical engineering from California Institute of Technology, Caltech. In 2000, he is a fellow of IEEE USA, IEEE India, and IEEE Distinguished Lecturer. His research interests include microwave, millimeter wave, and terahertz receiver systems and radars and development of space instruments for the search of life beyond Earth. He has more than 350 publications in international journals and conferences and holds more than 15 patents. He also received more than 35 NASA Technical Advancement and New Technology Invention Awards. He received the IEEE Region 6 Engineer of the Year Award in 2018. Distinguished Alumni Award from the Indian Institute of Engineering Science and Technology, IIEST India in 2017. He was recipient of the Best Journal Paper Award in 2013 by IEEE Transactions on Terahertz Science and Technology, Best Paper Award from Antenna Design and Application at European Antennas and Propagation Conference, EUCAP in 2017. The Best Journal Paper Award in 2020 by IEEE Transaction on Terahertz Science and Technology, and IETE Professor S.N. Mitra Memorial Award in 2014. So we are very pleased to host Dr. Goutam at this platform. And without any further delay, I request Dr. Goutam to please proceed and start the webinar. Over to you, Dr. Goutam.
Thank you so much, Dr. Shoaib. And I am really happy to be here today. Let me share my screen.
Yeah.
So let me play my So can you see my screen now?
Yes, I can see. I'm just sending it live now.
Okay.
Yes, it's live now. You may go ahead. Thank you.
Okay. So I'm really excited to talk to you all today. And this is the first time that I'm actually talking to, I could not be there in person, but at least in my through this webinar platform, I'm able to talk to you all. I'm really excited. I really want to thank Dr. Shoaib and my good friend Umar. Umar and I, we go back for a long time. I met him at different places, and there is some, some other kind of relationship that we have because Umar's grandfather and we went to the same place for for my PhD, that is the Caltech, California Institute of Technology. So we have kind of a different relationship. So that's why I'm really excited. So let's talk about are we alone? So what I am going to talk to you about that in NASA, what we do at NASA is one of the prime motivation for us is to actually answer to this big question, are we alone? And the technologies that we develop to answer that specific question and other science questions. So that's why I chose this topic, and I hope you all will enjoy it. So before we start, I want to acknowledge all my team members. The group that we have is called Submillimeter Wave Advanced Technology. We have about 24 people in our group, and if you look at the faces on these pictures, that you will see that they come from all over the world, including Pakistan. I have Dr. Imran Mehdi. He's from Pakistan, originally from Pakistan. So we have people from all over the world, and that's what makes NASA and our team great, because the amount of diversity that we have. When you have a team where people, they are the best of the brain from all over the world, then it makes a big difference, and that's why we have been so successful. So a little bit about NASA and JPL. NASA actually has different centers all around the country, and many of you know that our headquarters is in Washington DC, and we are here on the West Coast, Jet Propulsion Laboratory in Pasadena, California. JPL is one of the largest lab for NASA, and where we do all the robotic missions. And also many of you know about Houston, that is the Center, Johnson Space Center, from where we mostly do the manned missions for NASA. So here the robotic mission that we do, all the Mars missions that happens, that also we build it here. And we are going to launch March 2020 pretty soon, only a couple of days. We are planning to do that on July 30th. So that will be very exciting as well. So let's start. So this is the history of our universe. We call it the Big Bang Theory. So this is not the Big Bang Theory that you watch on TV. So this is the real Big Bang Theory. The history of our universe, we believe that the universe started with the Big Bang, and currently the age of the universe is about 13.85 billion years. So what happened is that we can actually study our universe in terms of electromagnetic waves. Light, like the optical visible light, is an electromagnetic wave. Similarly, there are many other forms of other types of electromagnetic wave, like your smartphone that communicates through electromagnetic waves. So we can actually go back in time and study the history of our universe in electromagnetic waves, but unfortunately we can go only go back up to about 385,000 years after the Big Bang, because before that no light came out from the Big Bang. The first light that came out is called cosmic microwave background signal, CMB. So that is very very interesting. There's some story behind that, how it was discovered, and after that, here we are. So we can actually learn a lot about our universe, how it was created, how it all came about, how stars, this modern universe, how stars and galaxies are formed, even being formed today. So those are the things we can study in electromagnetics. And people ask me this question very often, that are we alone? So let me tell you one thing, that we have not found life anywhere outside our planet Earth. That is the, let's say that, very clear, that we have not found any form of life anywhere outside our Earth. But the question is there possibility of life anywhere else? If you ask me that question, my answer to that will be yes, I believe there could be life outside our planet Earth. So what makes me so confident? Let's do some, back of the envelope calculations. If you look in the sky, you will see all these bright stars, right? All the twinkling stars in the sky. There are about 100 billion stars in our own galaxy, the Milky Way galaxy that we talk about. We have about 100 billion stars. That is about 11 zeros after 1. Then there are about 100 billion galaxies in our universe. So if you actually do your math, you'll realize that in the order of magnitude, 10 to the power 22 stars in this universe. And we are finding increasingly that many of these stars, majority of these stars, they have planets like our own sun. So they have planets around them, and not only one, they have multiple planets. Now the question is, what is the probability? What is the possibility that one of these stars has one planet where conditions are such that life can exist? You can, if you do your math, you'll realize that this probability is finite. It's not a zero. So there could be a star where there is a planet and there is life. And we are actually in search of those planets, and we are in search of, can we actually find, can we know more about them and find life there? You all know that NASA keeps going back to Mars and many other countries. This past 2 weeks, 2 countries actually, they have already sent 2 missions to Mars. One is UAE, Hope 1, and another one is China. They sent a couple of days ago, and then US is going to send it again on July 30th. So we keep going. What is the reason behind that? One of the reason is Mars actually resembles Earth in many ways, especially in its early history. The question is that, was Mars ever habitable? Because we have not found, as I said, we have not found life anywhere else. So we have not found any life, any form of life on Mars. But question is, was there life in Mars at any point of time? And what happened if there is no life today and life existed before? What exactly happened? Where did that go? So those are the questions we want to answer, and that's why we keep going back. So if I show you this picture and I tell you that this is actually one of the roads from my hometown in Kolkata during monsoon, you might say, oh yeah, it might be, but it's not. It's actually a picture from Mars. And if you look very carefully to this terrain, you realize that we get this kind of terrain only when there is flowing water. But when you go to Mars today, we don't see water. There is some water, but that is under the ground in terms of frozen water under the ground, but we don't see any flowing water. But you get this kind of terrain only when there is flowing water, which means at certain point of time on Mars, there is flowing water, but it is not there today. So the question is, what happened? Where did that go? Can it happen to our own Earth one day? And what can we do to prevent that? So these are the questions that we want to answer. We want to know more, and that's why we keep going back to Mars and know more about it. So we have gone to Mars, several times, and we actually landed rovers there. So if you look around 1996, the Pathfinder was small, cart kind of a rover. Then Spirit and Opportunity, 2 rovers we had sent in 2003. Then Curiosity was sent in 2011. They have done a really good job, Curiosity, and now we are sending the next one called Perseverance in March 2022. And increasingly, you can see that they actually gone bigger and bigger and more powerful. So the Mars 2020 Perseverance rover, it looks like this, and it has a lot of different instruments. So where I come in and we come in is actually we build the instruments that goes on this kind of rover to do science. So majority of the missions that we do, they have to have a science that drives all our technology development to actually answer big science questions. And I'll show you that, you can see that there are different kind of instruments. There are cameras, 23 cameras, and 9 are engineering camera, and 7 of them are actually science camera. They do science with 7 of these cameras. And this is one of the most recent picture that you will see. This is the Perseverance rover in our lab, all getting ready to go to Florida for launch. So this is more or is all done already now. We are really excited and looking forward to the launch. So this is a picture. I actually show this picture to students specifically. It was taken by Mars rover Curiosity, and if you look at that, this dot is actually planet Earth, and if you expand, you can see Earth and the Moon. So why this is the first time actually there's a picture taken from the surface of another planet of our own planet. So that is really exciting. So when you see this kind of pictures, we get very excited. If you have worked on those kind of missions, so that is the ultimate the thrill when you see that your instrument actually sending this kind of picture back. And more than that, if you can actually, that is a bigger point I want to make here, particularly to the students, because sometimes we think that, we have egos. We think we know everything, that we human beings, we know everything. We are so smart. But if you think about it, in the big scheme of things, we are just a dot in the sky. So next time, if you become a little bit cocky and start thinking too much and become egotistic, just think about this picture. Hopefully that will ground you. And many of you are electrical engineers, so you know that for electrical engineers, grounding is very important. So what are exoplanets? Exoplanets are planets that we are finding around other stars. So if you look around, we have actually found more than 4,000 exoplanets so far around other stars. We have looked in our own galaxies, and you can see that they're in shape and sizes. They're of all kinds of stars. There are giant, like gaseous giants like Jupiter. They have rocky planets like our Earth, and many of them. So we are in search of life and in that process, we are looking for planets which we call they're in the habitable zone or the Goldilocks zone. What do I mean by that? Habitable zone is that if we find a planet where the temperature is such that water can exist on the surface in liquid form, then we call in the habitable zone. Because when you're looking for life, that we always look for the kind of life that we know about. And the kind of life that we know about is the carbon-based life, which needs water, which needs oxygen. And that's why we actually look for planets in the habitable zone. They have to be rocky planets. The temperature has to be correct. So that's what we have been looking for. And we actually have found quite a few of the planets where they are in the habitable zone, they're in the Goldilocks zone. Unfortunately, they're kind of far. Like we found one system of planetary bodies, it is about 40 light years away. And if we use our current day technology, it will take about 40 million years to reach there. So we won't be able to go there in our lifetime. So what we'll have to do is we'll have to study about those sitting in here, which means we'll have to build new instruments, more sensitive instruments, and that's what we are actually doing right now, try to understand more. So how do we find these kind of planets? So if you look at that we actually, if people ask me that I said that there should be about 10 to the power 22 stars, then why did you find only 4,000 planets? The reason is we actually have not looked much. So far, if you look around, we have looked only about very narrow area of our own galaxy because we didn't have the technology. We need much better technology to actually look at much farther places. And How do you actually find those kind of planets? This is one of the ways. It's called transit time detection method. What happens is, first of all, we look at the stars, and stars, they're giving out lights, and we'll have to first isolate one of the stars. And once we do, and if you look at that, if we measure the total amount of light that is coming from the star, and if there is a planet that is going around the star as you see on the top right of your screen, then what will happen is, as the planet goes in front of the star, the total amount of light reduces ever so slightly, and then we can actually measure. I can actually say there is a planet. And by measuring, how much time it takes to go in front of the star, and we can actually study a lot of things. What is the size of this star, and how far it is from the this planet from the star, and whether it's a rocky planet or not. So a lot of things we can do by studying from here. So another way we can do is called the Doppler method. What happens is that if we measure a frequency that is coming from this star, and as the planet goes in front and away from this star, the frequency changes because of the Doppler effect. And by measuring the change in frequency, we'll be able to tell, yes, that is a planet. But it gets complicated whether multiple planets going around. So it is not as simple as I am actually showing here. It's much more complicated. Much more complicated, but you get the idea that how we do this. So another thing is, as I said, the kind of life that we know needs water. So is there water out there? The answer is yes. We are actually finding, one of the instruments, the Herschel Hi-Fi, I was involved in developing this technology for Hi-Fi instrument. We actually built that instrument. So we found that in young sun-like stars has a lot of water coming out. These water molecules are coming out in a very high speed. It's like what high speed? About 200,000 kilometers per hour. So if you fire a bullet from an AK-47 rifle, I'm not suggesting you do that, but if you do, the speed of that bullet is about 2,500 kilometers per hour, which means these water molecules are traveling 80 times faster than an AK-47 bullet. And then what happens if something is traveling that fast? It creates a lot of heat and it tends to destroy, but the conditions are such that it finds a way to recombine and produce huge amount of water. How much? About 100 million times the total water on the Amazon River is formed per second in one of these stars, which means this universe is flooded with water. There's a huge amount of water out there. So if there is water, can there be life? So that's what we are actually looking for. Another thing is about water is that when Earth was formed, then there is no water. And scientists believe that comets actually brought water to Earth. And then if I tell you that, then you say, oh, I don't believe you. How do you actually prove that? So we are actually building a lot of instruments. We have done few measurements on some comets where we actually measure the ratio of different kinds of water on those planets. And actually currently I am building some instruments on a shoebox size, on a CubeSat, to go to a comet and do measurements to actually answer this question. That if we know that, then we'll be able to figure out, how the water comes to other planets as well. So if we think about that, we are thinking that, okay, is there life outside? As we said, we are finding exoplanets and we are trying to find life there. But is there a possibility that there could be life in our own solar system? So we are also finding a lot of exciting things. That this is the picture of Enceladus. Enceladus is a moon of Saturn. And what we find that by Herschel Observatory have found that what you see here is water coming out, gushing out from here. If you expand this, we'll see water coming out. So if this is a cold body, if the water is coming out, that it has to have some source of energy that is making, this frozen water to liquid water that's coming out. And the question is, is in this water, what are the other things out there? Can there be any life forming elements? Can there be any organic elements? Is there life in that? So NASA is actually planning a mission. We are actually thinking about it to go to Enceladus and try to find out, what is going on there, what is in there in that water. Another place where that could be life that's very exciting is Europa. Europa is actually a moon of Jupiter. Jupiter has multiple moons, like our planet Earth has only one moon, but Jupiter has multiple moons. And this is a very icy planetary body, Europa. And we believe, the scientists believe, that there is a water ocean underneath Europa's, the surface. And this surface, this about ice, about 15 to 100 kilometers deep, and then there is a liquid water ocean. If there is a liquid water ocean, that means there has to be a mantle, the source of heat that is keeping this water liquid. And NASA actually is planning a mission to go there in 26 time frame to measure, to find out if there is what is happening to Europa. Is there a possibility of life? Now, if I tell you that we are actually sending a mission to Europa, and what kind of instrument that you are going to build to actually find that if there is life. So of course, the obvious answer is that we'll send a drill, we'll drill a hole and lower a bucket and take a bucket full of water and see if there is fish there, right? But problem is when we have this kind of mission, we have only about 300 to 400 watts of total power available. So 300 to 400 watts is 3 to 4 light bulbs, right? So how can you it turns out the thickness of this ice is about 15 kilometers to 100 kilometers. So how can you drill a hole 15 kilometers deep through ice with 400 watts of power? That is not going to happen. So we'll have to think outside the box and come up with solutions that we can measure what is out there. So we are actually building a lot of instruments to do that. It turns out that there are a lot of cracks, and these materials actually goes all the way to the top through these cracks. And once they reach the surface, because it's so cold, it freezes. But Europa is very close to Jupiter, and Jupiter has a very high magnetic field. What high magnetic field does, it creates a lot of high radiation environment, and the radiation actually sputters all the material to the top surface, from the surface to the atmosphere, and we can actually measure the atmosphere through spectroscopy to find out is there any organic material. So we are planning to build instruments to do all those. Now, I told you about all these different kinds of the science ideas that to find life to far off exoplanets as well as in our own solar system. But what kind of technologies that we need to do to build to address them? To build instruments, we'll have to make things really small, low power and low mass, because every kilogram of mass that we send to an outer planet, to far off place, it costs a huge amount of money. And also the propulsion that we need to send it out gets more and more if things become heavier and needs more power. So we'll have to make it smaller and smaller. Miniaturization is the key. So we have been actually very good in miniaturizing things like this, that if you look at this, first IC that was built in 1960 had 3 to 4 transistors. And then in 1969, the SRAM, 256 bytes of SRAM that we did in 1969 had about 2000 transistors. And if this is the NVIDIA graphics chip, has about 7 billion transistors. So we are actually really getting better to make more functional chips, ICs, with more number of transistors. So we are actually producing about 10 to the power 19 transistors per year, 1,000 times per 1,000 transistors per every ant on planet Earth. I don't know why I put that, statistics, but majority of these transistors work. But that is not enough. Just making an IC does not make an instrument. So you have to actually think about how we integrate them, how we actually make an instrument out of that. Look at this, that Federal's 1 megawatt pulsar arc radio transmitter in 1917 was such a huge instrument. And you know what this one is on top right of your screen? That is actually iPhone 5, the entire circuitry of iPhone 5. And if you look, if damage and okay, can you hear me?
Yes, yes, please go ahead.
Okay, because can you see my screen?
Yes, yes, I can see.
Okay. All right, sorry, because I had lost connection. So
No.
here, what I was saying, that if you actually have not opened your smartphone, you should open, and you should see that is a beautiful engineering. The number of chips, how they are connected, what the interconnects are, what the all these connectors is a big piece of art. And we are trying to do in NASA. We are actually trying to build instruments using the iPhone technology. And we had made a lot of progress in that direction. And as I was mentioning, we are actually focusing on small satellites. They are called CubeSat and SmallSat. They are shoebox sized satellites. The size of them is actually 10 centimeter by 10 centimeter by 10 centimeters, called 1U. We are building about 3U or 6U CubeSat, and already there are many CubeSats out there, and many more planned. So what happens in the CubeSat world is that we can actually miniaturize everything, and the cost of these CubeSats is much less compared to big satellite. As a result, we can actually build many more. Of course, we'll have to compromise in terms of functionality, but we can still do very well. One of the first CubeSat that we sent to Mars is called Marco, along with the InSight spacecraft. So what happens is, when you go to Mars, as the spacecraft enters the atmosphere, there is no communication, because there is no direct link to Earth at that time. So first of all, it takes 7 minutes for signal to come from Mars to Earth. On top of that, if there is no line of sight, so whether our rover or the spacecraft actually landed or not, we don't know. We do not have any live feed going on because there is no direct connection. So to avoid that, what we did for this mission is that we actually made this shoebox size. These are 6U, that means 30 centimeter by 20 centimeter by 10 centimeter CubeSat, and it had 2 antennas. One of the antenna is actually UHF transmission that transmitted from here to the spacecraft. It was communicating, and then it had an X-band receiver using reflector array antennas. You can see here on the left bottom, this is the reflector antenna in X-band, and it has a direct DTE, direct link to Earth. So that's what was transmitting, from getting signal from the spacecraft and relaying it back to Earth in real time. So that's how we actually knew what is happening as the spacecraft was going down. So also we built some more CubeSat based antenna. This is a rain cube. This is an animation showing the rain cube antenna. This is a 50 centimeter deploying antenna. So you can see that we'll have to have deploying antenna, because if the volume of this is so small, we cannot have a large antenna connected to that, but we need bigger size antennas to get data. So how do we do that? So we actually came up with a very good antenna. My colleague Nasser, he was my postdoc. So we actually developed this antenna, K-band deployment rain cube antenna. This actually, I'll show you how we deploy it. This is a very innovative idea. This is a reflector, parabolic reflector. I'll show you how we deploy it in the lab. So this is spring-loaded structure. There is a video. I hope the video works. As we press the button, then what happens is this parabolic reflector deploys. This is a mesh reflector. This K-band, 34 gigahertz. And then we had to have the subreflector deploys as well. And then it actually worked really well on RainCube. So we'll have to actually innovate. We'll have to come up with new ideas, because here think about it. We have space, very limited volume available. So we'll have to fold everything in and then deploy this antenna. So we are building even larger reflector antennas, 1 meter, and we are going higher frequencies as well. So we believe that future is flat. So we'll have to build antennas that goes on the side walls of the spacecraft itself. So in that process, we developed some metasurface antennas. This is a 3D printed metasurface antenna. I call it fakir bed antenna because these are all metal pins that they're sticking out. And so this is a K-band antenna that we built. This is about 20 centimeter in diameter. We are trying to make larger as well, and we are making 90 gigahertz as well. So there's a lot of the thickness of this total antenna is about 1.5 millimeter. So you can think about, and it's fed through a circular waveguide at the center of this. So there is no feed like reflector rays. You need a feed, but here we don't have a feed. So this is just a circular waveguide at the center, and that's how we feed it. So it is, you can go on the side. This is all metal structure, so you can go on the side wall of the antenna, and that itself acts as an antenna. This is a very good concept for this kind of missions. So we built a 300 gigahertz such antenna that worked using silicon micromachining, and as you can see, the metal pins for these 300 gigahertz about 115 micron. So just thickness of your hair. Generally, the thickness of your hair is about 50 micron to 200 micron. So that is the antenna. So really low profile flat antennas that we are actually developing. And with that, as I said, that we are actually building an instrument to go to a comet to find out if comets brought water to Earth. So I am currently, as a PI, we are actually developing this instrument called What's Up, a water hunting advanced terahertz spectrometer on ultra small platform, because we want to know what's up with water, what is going on with water, how water came to Earth. So this is a 500 to 600 gigahertz spectrometer instrument. So this is how it looks like. This is the block diagram of this instrument. We will be measuring all different frequencies, and then this is how it looks like. This is the antenna that we are going to use, a very low profile antenna, and this is very compact instrument. And we also have a silicon micromachining system built in that for calibration. And so when you put everything, we actually, as I said, we actually have used SoCs, the system on chip based W-band synthesizer, SoCs W-band synthesizer, very low amount of power. Off the shelf synthesizer for these frequencies, W-band will draw about 8 watts of power. But the SoC synthesizer that we developed, it draws about 150 milliwatt of power. So you can save huge amount of power. Also, we build the spectrometer chip itself. The entire ASIC chip does 4,000 channel spectrometer. So that is a very, very powerful chip and drawing about 1.5 watts of power. So saving power and making everything small and compact is the key for the future missions, for planetary missions. So I have put these things together. This is how it looks like. This is the one. It weighs the entire instrument weighs less than 2 kilograms and draws less than 5 watt. Think about it. 5 watts is your night lamp. That's 5 watts. So that is the entire instrument. So that is what we are doing in our lab. So I will actually end because I want to keep more time for question and answers. So I will end with this, that many of you know that we have decided for March 2020 to have a helicopter called Ingenuity, the name of the helicopter. So why helicopter is a big deal? The reason is that when you have a rover, so the rover goes there, as I said, it takes about 7 minutes to a signal to reach to Mars. So we cannot really do an online driving for the rover. So we'll have to actually upload all our information beforehand, and then the rover will go where we want it to go. So, however, if now we have a helicopter actually that is on the rover, and then the helicopter can take off from the rover, go around, it will have sensors on the helicopter. It can send those signal back, and then based on the signal that the rover receives, it can decide where is interesting things are happening, so they can go there. So that is the idea. The problem is that making a helicopter for Mars is much more difficult, because if you think about it, because Mars atmosphere is much lighter than our Earth's atmosphere. So here, if for a helicopter, the speed of the blades are about 400 to 600 RPM revolution per minute. But for a helicopter to work on Mars, it actually needs 2500 to 2600 RPM. That is huge difference. It has to be really lightweight. And how do you power them? You cannot slap a big battery on that. So because it has to be lightweight. So we made a lot of innovative ideas and made a very lightweight helicopter. On top of that, one challenge was it had to send signal back, right? It need to have antennas. And then these are on metallic blades. These blades that are used, they are very much like metal. As a result, when the antenna was put, we found these blades are actually messing up our antenna radiation pattern. So we had to really come up with new ideas to solve those problems, but we have been successful. And I'll show you, this is the picture of the Mars helicopter Ingenuity that is getting ready to be integrated on Mars 2020, the mission. So it's all ready to go. So let's keep our fingers crossed. So July 30th is going to get launched. So with that, I'll end, and I'm excited to take questions from you all.
Thank you very much, Dr. Goutam, for your very interesting talk. Today I found some very interesting ideas as well. I think I should appreciate you and your team that are working on very novel ideas, very bright ideas to explore the outer space. So one general question is that, for example, the countries which are underdeveloped or developing countries that especially struggling with the budget. So how can they participate in this outer space mission?
So one of the things that I talked about these CubeSat missions, if you look at the CubeSats are not very big, they're shoebox size. So majority of them is about, as I said, 30 centimeter by 20 centimeter by 10 centimeter. So one of the way to do that will be to actually develop instrumentation. You have to have an idea of what exactly you want to do, develop that instrumentation, and NASA and other space agencies, they are willing to launch, even some private entities nowadays, they're willing to launch these CubeSats. So students, majority of the, in the United States, majority of the CubeSat instruments are actually built by students, undergraduate students. So their projects. But NASA, when we actually do a real mission, real scientific mission, of course, then we'll have to pay much more attention and we have to focus on doing real science, so that it gets a little bit complicated at that time. However, to do many of the things, the students can develop CubeSat-based instrumentation and approach some of these space organizations, and they're willing to launch those CubeSats.
Thank you. I think you are very right. Here in our country, we should conduct some competitions, some thesis, some final year projects based on these ideas or other innovative ideas, so that we can also contribute in the future missions as well.
Yeah, absolutely. And I want to mention that IEEE MTT Society, Microwave Theory and Technique Society, right now they have a competition going on. They will provide money to the teams, the students, and IEEE members to actually come up with an idea to build CubeSats. So if you go to mtt.org, and you should actually check and take part in those competitions, then you will get some kind of support to build your instruments and ideas.
Yeah, I also suggest the attendees and participants to please visit the MTT website and fully participate in such events and such competition. This will make our skills much better, and also is a very good learning experience. So I go to the question from audience. The first question is, if we observe from season that explain us a little change in the distance between the Earth and Sun bring a lot of change in weather, So is there any probability that having a planet with a very precise distance from the sun is quite low?
It's not. It need not be the same distance as the sun and Earth. What we require that it will all depend on what is the size of the star that we are talking about, what kind of luminosity it has, and then depending on that, how far that planet needs to be so that the surface temperature is such that the water can exist. And also, we are finding that some of these planets are actually tidally locked to the star. What do I mean by tidally locked? It's like our moon. You all know that moon is actually tidally locked to Earth. As a result, we always see the same face of the moon. So we do not see the other face of the moon. We always see the same face. So some of these planets we are always looking at the same face of them is looking at the star. As a result, that one side is one temperature and the other side is a different temperature. But as a result, so one side is habitable, other side is not. So it's very interesting. A lot of interesting things we are actually discovering every single day.
Yeah. That's very true. Another question is, recently I have seen on news channel, this is a question from an audience, that there's a blue glow around the Mars as of Earth showing oxygen. Is it true, or up to what extent?
No, we have not found. That is not true. It is not true that we actually found all this oxygen and all. We are looking for like methane is one of the thing that we have detected in low level of methane. We are trying to figure it out. What is the source of that? Because that could be an interesting thing. That what is the source from where methane is coming from? So there are a lot of things to be explored still. But again, we have not found any sign yet that those are present.
Thank you. Another question is, to gain the benefit from the probability that life exists beyond our planet, how NASA plans to overcome the problem of reaching places that are many light years away? What level of innovation?
Very good question. So we all need you. All of you need to come and help us to develop the new technologies so that we can have the technology to go to far off places. Right now, we don't. Like even going to Mars, we can send people to Mars, but we cannot bring them back. So it's a one-way ticket. So that is the situation we are in. So to go to far off places is a long way, but we should not give up hope, because who would have thought that we'll be able to go to Mars like say 50 years or 100 years ago. So things change very fast and new technologies coming in. So we'll have to keep investing in new, these technologies, new ideas. We'll have to invest in the human resources, because you are the future human being. They are the one, they are going to come up with new ideas. So all of you, the students, you are our future. So we are looking at you to come up with new ideas so that we can go to far off places.
Yeah, you are very right. The technological advancements are going exponentially very fast. They're growing, and we can expect anything at any time. Yes. Many years ago, nobody ever think of going to Mars, but now many countries are participating in this mission, which is also very encouraging for the space exploration programs. There's interesting question that are UFOs, unidentified flying objects, are real? Is so, does this mean alien have been visiting Earth all along?
So okay, I expected this question, because whenever I give a talk, these are questions about UFO, Area 51, or the moon landing was fake or not. These kind of questions are asked. So what are UFOs? UFOs are unidentified flying objects. So majority of the time, if you actually find something that you cannot identify initially, and if you start thinking about it, and then you can figure out what actually happened, what is the phenomena. And so we have not found aliens. Even if they came, we don't know. So if you find anyone, let us know. It will be very exciting, but we have not found any. So UFOs are, whenever you see something, when you read about something like that, if you start paying more attention, you actually start thinking about it, you will realize that most of the time it is at some known phenomena, or the physics can explain them.
Right. So the next question is, what is the role of RF engineer in designing instrument at NASA, as mentioned before, engineering cameras? So I think he's talking about the role of an RF engineer.
Can you hear me now? So
yeah,
we
yeah.
actually lost that connection for a second. So the question was that what is the role of RF engineering? Is very important role, because RF plays in many ways. One of them is communication, because at the end of the day, when you gather data, what we do at NASA or what we are trying to do is try to get scientific information, and through some sensors, through some detectors, once you get those information, that can be of any frequency band, those sensors, but they will have to send the data back. And most of the time we use RF frequencies to send the data back. What frequency band do we use? X band, about 10 gigahertz. We use K band, that is 30 gigahertz range. So even low bands, L band, S band, we have all those frequencies, they're all RF. And on top of that, we actually build instruments, RF frequencies going all the way from low end megahertz to terahertz band. So we build all different kinds of instruments. So RF engineers are very, very important. So if you are working at RF, you have a bright future, because we cannot live without RF.
Yeah, that's very true. And some of few examples you told about the antennas, especially different type of antennas. I think RF and also the RF front end and transceiver. I think RF engineer can play a very vital role in developing some new and innovative instruments and equipment. Yeah. The next question is, why don't we use solar energy rather than fossil energy for our rovers? We might be able to get enough energy to drill holes.
So if you think about it, Mars is much further away from our sun than our planet Earth. So amount of solar light that's reaching there is not as much as we are getting here. On top of that, solar energy means you need larger solar panels. So larger solar panel that we have to send it to Mars. How do you send huge solar panel to a small rover? So that is the challenging part, right? So you cannot really generate, and think about, we are talking about going to Europa. Europa is even further, hardly any sunlight goes there. So amount of power that we can generate with this reasonable size solar panel is not that much. Unfortunately, that's the reality.
Yeah, also, yeah, you're very right. The weight of everything matters when we talk about the space.
Yes.
And you have shown some examples that we have to develop the instrument that should be very, very lightweight, because it's consume energy and everything, and it's a very challenging task. The next question is, I think the question is relative to this the same question. I think they are talking about the Europa mission, that why don't you take the molten lava in some safe place, some safe way on Europa to make a hole?
So molten lava, again, how much lava that you will need? How are you going to carry it? As I said, total amount of mass that you can carry is very limited. Total amount of power that you can carry is very limited. Sometime back someone said, why don't you just do a nuclear, something, and drop nuclear powered some stuff so that it goes down and it creates that heat and melts that ice. Problem is you don't want to destroy the planet to life that exists there to find life. So you cannot do many of those things. So that's why the challenge is.
Yeah, you're right. There's another question. Where do we stand on Hubble constant discrepancy?
Yes, it's a good question. You know what? Many of you who don't know, this Hubble constant is actually, as the universe is expanding, right? So there is a constant that actually defines, what is the speed of expansion and what is that number. So there is a discrepancy in the sense that we are improving that number with time. That's what happens. But if you look at the Hubble constant right now, we know. Scientists believe that we are pretty close to what it is, through measurement. But again, we'll have to fine tune. Things change as we have more and more information. So that's how the science works, right? Because we do observe, do make new measurements, and then we can actually fine tune those numbers like Hubble constants.
Right. The next question is about the piezoelectric technologies. That piezoelectric technologies could be much helpful for providing electrical energy to the system.
It does not produce a lot of power. If you look at the piezoelectric stuff, that we actually use some piezoelectric technologies to make motions, in the sense to scan things very small scale, because you cannot really generate a huge amount of power, because you have to see that what amount of mass you need to generate certain amount of power. So if we know that in terms of efficiency, our solar panels are much more efficient compared to what you get on the normal market. So we have our solar panels are about 40% efficient, 40 plus. But if what you buy in the market, if you put a solar panel on your rooftop, that is much lower, like 18 to 20%, because our things are much more expensive. Majority of the other way of generating power is very low efficient.
Right. The next question is it possible to send large amount of oxygen to Mars?
Oxygen to Mars?
Yeah.
Large amount of oxygen? Of course, it all depends on what exactly you want to do to, with your mission. You can send some amount. You cannot send a large amount because, again, we are limited by how much we can send. And then, I mean, if you are planning to do a colonize Mars, that's why I need oxygen. I don't know, because if Mars is not a very nice place to live, or our Earth is much better place to live.
Yeah, yeah, we are very lucky that we have a planet like Earth, which has so much diverse properties for life to exist. I mean, the other planets are very. I mean, there are very few properties. There are very limited chances that the life exists there. But as you mentioned, we should explore, because everything a mission is done. It's not just the way of that somebody is going to Mars, but also the technological advancement that help the humanity is very important. Yeah. So sometimes I also think that why a country is spending a huge amount of money to send the mission to outer space. Why not they spend money on to people on Earth? And again, I heard from by discussing with some professors that they told that you can imagine how much the technological advancement you get from one mission.
That's
just
right.
One mission.
Yeah, I'll give you some examples. I will, like, can you live without your smartphone for a couple of days? People cannot, right?
I guess, no.
And many of those technology that has been actually in your smartphone has been developed through the space programs and other programs. So we have to actually there are a lot of other advancement happens when you actually spend money in real research, as well as scientific research, technological research. So we'll have to always spend money, to those. We can ask, why do we need pure science? Because pure science also gives us insight into what we can do, and that's why we make advancement. So it has a lot of other benefits as well.
Yeah, you were very right. The next question: how important is antenna design for mission to Mars? I think
yes, of course, antennas are important, as I said, from communication side. Think about it, that we cannot make very large antennas, but we'll have to make efficient antennas. How do you make deployable antennas, so that we can establish the communication link? On top of that, if you are talking about some question was RF, how important is RF? RF means you need antennas as well, right, to actually capture the signal, and you need more efficient antennas, innovative antennas, new kinds of antennas. So antennas play a big role, like everything else, like RF front end plays an important role. So every part of your instrument actually is important. So you can if you can improve every single areas of that, only then you make real progress.
Yeah, there's also encouraging for RF engineers as well to participate in this mission. The next question is, all these ideas are related to electronics innovations, but what is the mechanics and designs which should be developed when actually NASA required for its missions?
So actually in NASA, we have people from all different backgrounds. We need everyone because, you know, a mission is just not just RF electronics, it's not just antennas, it's not just RF front end. It is about mechanical, it's about thermal, you know, every single aspect of engineering actually comes together. That's why, you know, our workplace, Jet Propulsion Laboratory at NASA Jet Propulsion is such a wonderful place to work. The reason is people of all different backgrounds, all different engineering backgrounds are working all together. You know, my next door office mate is actually a mechanical engineer. Someone else is a thermal engineer. On top of that, someone is actually a physicist who are actually trying to figure out someone is a chemist, a biologist, because astrobiology is also important. If we find some form of life, you know, somewhere, then we need biologists, we need chemists. So we need people from all different backgrounds. And so it does not matter if you are good, then we are open to you because we want you to come and work with us. So in all different disciplines. So that is the beauty of an organization like NASA.
Dr. Goutam, one of the things that when we work in such a large and very critical projects is the team management, and as you mentioned that there's a lot of diversity in the system. So how NASA manage the team? I mean, taking inputs from all of them and then integrating them. So isn't it a very challenging task?
Yes, so you know, managing is, but you know, you have to do. That's why I said not only we need, you know, managers as well. So you know, a lot of engineers look down upon managers, but managing a big project is not easy because you'll have to all the small, you know, nuts and bolts to be, you know, come together, and they'll have to execute that project within the given time, schedule, and the budget. So these are all different things. So you'll have to, that's why we need people very smart, people who have this managerial skill, who actually understand the schedule, who understand the budget process, who can actually bring all this, you know, interaction between different teams, because one is working on one area, another team is working in a different area, how the interface, because if the interface does not work well, then there'll be mistakes. Mistakes are made, and then to avoid those kind of, and one new problem is you know, failure is not an option for us because if we cannot go back and fix it when you launch something. So we'll have to make sure that everything works at the first try. So that's why all these aspects are very, very important.
Yeah, that's very true, because the success of a mission is not just technical part, but also managerial part is also very, very important. The one of the question is how the NASA, is there any possibility that NASA has some funding for different countries to develop the system, or I don't know, to collaborate with the other countries?
So yeah, NASA is willing to collaborate. Only problem is that, you know, like other countries, NASA cannot send money. We cannot send money to another country, like other countries cannot send money to us. So what happens is that when we do collaboration with other countries, like, you know, Indian Space Research Organization, ISRO, so there is a lot of good, you know, collaboration is going on with ISRO and NASA, as well as, you know, ESA, European Space Agency, and NASA. So what happens is that when we are sending a mission, then we open it up for everyone to say, okay, do we want to contribute an instrument? So, and then what they can contribute an instrument. So they build that instrument, but of course we will provide the guidance in the sense that, okay, it has to all the interface documents and everything, but they'll have to spend their own money to develop that, and then it will go with that mission. So yes, so those kind of collaboration is happening more and more because these missions are getting so large and so expensive. It is very difficult nowadays to actually one country to do multiple missions. So if we can collaborate, international collaboration is very important for space missions.
That's very correct. Another question is, for example, if, for example, NASA is also sending the mission to Mars and other countries are also sending the mission to Mars. So is it necessary that every country should send a separate mission to the Mars, or so what's your comment on this?
So you know that If they all combine hands and actually do jointly, that is better. But of course, every country has their own ambition and own ideas. So you cannot really tell that only one country will do or not the other country. So, but at the end of that, you will realize they actually come together. That is true. But once you have demonstrated, like for NASA provided the Mangalyaan mission for ISRO, NASA provided the Deep Space Network and the health. So we'll have to all help each other and collaborate with each other to be successful.
Thank you very much, Dr. Goutam. I think it's already 11 p.m. at your side. It's a Sunday night, yes. And we are very thankful to you that you spared the time at this moment to deliver a talk to the audience, of especially to the audience of Pakistan. And I got very positive feedback from the audience as well, from the comments and those questions that are really encouraging. As you know, next year we also planning to host a conference in Pakistan. We will be very pleased to host you in Pakistan as well. Before that, we can also arrange more webinars or more live talks or presentation if this COVID finishes. I hope this COVID will end soon. So thanks again. Thank you very much for your very interesting talk, and I think very interesting question answer session as well.
Thank you so much. I really enjoyed, and I wish, as I said, I'm looking forward to meet you all in person one day, and we'll overcome COVID, of course, and then when you come out of that side, and hopefully you'll be able to travel. And again, I really thank all the people who joined in from Pakistan, especially, and it was exciting and a lot of things to do, and we need help from all of you. So we need you. That's the key. The message that I want to give, that this is this world is all all connected together. That is science and technology does not know any boundaries, and we need everyone to collaborate, and that's how we make progress. That's how civilization make progress. Human beings will make progress that way. This through collaboration. And thank you, and stay safe and maintain social distancing. Wear a mask. Thank you very much.
Thank you, Dr. Goutam. I 100% agreed that the science has no boundaries, and science can't work in isolation. We should work together to make the life better here and also in the outer space. I would like to mention that our team and Dr. Umar, our principal engineer Shahid Niaz, also sending thanks to you for your time and this interesting presentation, and hope to see you again very soon at either in live webinar or physically you in Pakistan.
Thank you. Thank you very much. Have a great day.
Thank you. Okay. Have a nice night. Bye bye.
Okay, bye.
Bye. Thank you.